Okay, we can start today. I would like to start by clarifying something I said last time about regular rings. So this is the thing. So the definition of regular ring is as follows. So R is regular if two things happen. First, R is Noetherian and Rp is a regular local ring for all P. Okay? And so in the local case, this can be understood in three ways. So we have that the maximal ideal of this ring, let's say PRP, is generated by a regular sequence. And the other one was that, let's say, the projected dimension of the residue field here, which I'm going to denote by Kp or kappa p in this ring, is finite. Okay? Actually, you can even say, well, finite, or in that case, it's necessarily actually equals to the dimension of Rp, which is a finite number, because R is Noetherian, so Rp is Noetherian, and Noetherian local rings have finite dimension. Okay? So, these things here can be generalized as follows, outside the local case. So, okay, let's say, then you can have the following proposition. So, if R is Noetherian and has finite dimension, which doesn't follow from Noetherianity, okay? It's a famous example by Nagata, but in the local case, it would follow. Okay? Then we have that R is regular if and only if the global dimension of R is at most the dimension of R. And remember, this means that any finally generated R module has a free resolution of length of most dimension of R. And you can simply say that the global dimension is finite. Okay? So, and I was saying that if you want, you can say, okay, maybe there is a good definition for regularity, which drops this hypothesis here, or something like this, or no, we should drop Noetherianity and you say that the global dimension is finite. But that's too restrictive because that would imply that the dimension of R is finite. So, but you also want to include a priori infinite dimensional rings as part of your definition of regular ring. Okay. So, saying that a ring is regular if and only if it has finite global dimension is only a good definition if your ring has finite Krull dimension. Okay? So in general, what you do is that you assume that R is Noetherian, and you assume that locally you have regular local rings. So I'd like to mention this because it's going to come up later, hopefully towards the end of the class. Okay. So any questions with this? So, okay, now you know what a regular ring is and how you can think about it in different contexts. Okay, so I told you to read section 1.4 last time, but I think I'm going to go through it because it's going to be important today. So section 1.4 is about complete regular local rings. And the Cohen structure theorems. So I won't be adding the proofs just yet here because it would take me so much time. But I recommend strongly to read, if you want to really understand how this works, to read the notes by Huxley. I'm gonna put a link on my website to them, or also in the notes. I forgot to do that. Huxley's notes. I think the name of the notes is something like the structure of complete local rings. And as you may expect, the notes are absolutely amazing. So it's a very good thing to read. So did you study complete local rings in your community algebra course? But it's definitely not a standard thing, more or less. Okay, more or less. So what we need to know is the following. We're going to be using it a lot, so maybe it's a good idea to remember how it works. Okay, so the first thing to do is to take a Noetherian. Remember, everything is Noetherian here when it is local ring. For the definition, Noetherianity is not needed, but if you want to have a good property, you need things to be Noetherian. Okay, so then we have the completion operation of the ring. Completion. It is a ring homomorphism. So you construct a bigger ring. I'm going to denote it by r hat, and by definition is the following limit. So you take a limit over these things. So you start with r modulo m, which is the residue field, and there you have r modulo m squared. Right? You start doing like thickenings around K, the close point of the ring, right? So 3 and so on. So you start doing these thickenings around the close point, and these are supposed to represent like this infinitesimal neighborhoods around the point. And when you take the limit, you get this local ring. Okay, so if you want to know what an element of this ring looks like, right? It's going to look like a sequence of A0, maybe not A0, no, A1 perhaps, A2, A3, and so on. And the point is that AI belongs to R modulo M to the I, but they have to be compatible, right? So if you take A3 and you reduce it modulo M, right, you're supposed to get A2. And if you take A2, reduce it modulo A1, and you're supposed to get A1. So they're supposed to map to one another, right? So that gives you this well-defined ring that is called the completion of R. So let me write down some properties here that would be proved in a computer algebra course ideally. So facts. Very important facts. So R hat is a Noetherian. So Noetherianity is to start. It is a local ring with maximal ideal. So to get the maximal ideal of this ring, let's call it M hat, what you have to do is to extend N across this homomorphism. Oh, and you may be wondering how this works, right? Maybe I didn't say that, but it is by the constant sequence, right? Like you can take A here, and you can send it to the constant sequence, right? Or its class in this portion, right? And this is a compatible sequence, right? Because A modulo N is A and so on. So you can do this, and this is the maximal ideal of R hat. And the other good thing is that you preserve the residue field. R hat modulo M hat is K. So in particular, this is a local map, right? Like the maximal ideal extends to the maximal ideal, or it's inside there. Or in other words, the maximal ideal here contracts to the maximal ideal here. And the other fact, which is also really, really important, is that this map here is faithfully flat. In other words, if you want, for example, to show that a module is 0 here, you can do a base change and try to prove it's 0 there and things of that type. Or you know all this theory about flat descent, right? When you want all these properties that you want to verify, what you can do is to do a faithfully flat base change, right? And if you can prove the property there, you can descend it to the original ring. So that's what we're going to be doing a lot. And we require this property here, okay? That we are always doing faithfully flat base changes. Is that okay? So I'm not claiming these are obvious things at all, but these are facts that we're just going to take as a huge black box. And but you can read everything here in this Hofstadter notes, and it's all great. Or you can take any standard commutative algebra textbook, say Atiyah, McDonald. What else is there? Matsumura. It's all there. Okay, so that's the process of completion. Did I define what a complete ring is? I don't think I've defined it, right? Actually, for example, using that property I just mentioned, you can prove that the depth. Maybe let me say something else first. Well. Yeah, maybe the other thing I wanted to say is the dimension of R is also the dimension of R hat. Dimension doesn't change. And actually with this, you can do as an exercise, this is definitely not difficult, that R is irregular if and only if R hat is regular. So the regularity property is stable under completions. Okay? So other facts, for example, this is an exercise. The nodes of the depth, it's invariant. And with these two things together, you can see that R is Cohen-Macaulay if and only if our hat is Cohen-Macaulay. So there's an example. This one you can prove. Actually, it's not extremely difficult. But how does completion work? So for example, if I give you a ring like this, right? I can give you some polynomial ring, variables, and relations, right? So you may say these are all the rings I care about, right? These rings of finite type, right? So, and let's take a maximal ideal here. Let's take the ideal generated by the variables. So more geometrically, we are looking at the origin, right, of this affine variety. And well, I'm going to assume that this, well, otherwise this is kind of trivial. So let's say that all these polynomials vanish at the origin. So there are m of them. Okay, and so we can take this local ring, we localize R at m, and we can try to see what is the completion of that. And so what this is, all we have to do is we look at the exact same expression. We have variables, we have polynomials, and all we have to do is to consider power series instead. So remember that this ring here is the ring of formal power series. So what is this ring? Well, let me tell you what it is as a K-vector space. So I'm going to tell you that first. So as a K-vector space, so the polynomial ring is a direct sum. So the polynomial ring is a direct sum, like this, right? Like, so you have n variables, and you take powers here, and then you let all these coefficients here, so all these exponents to be natural numbers, right? So these are antiples, right? That's the polynomial ring. It's a direct sum like that. Right, it is a symmetric algebra over the vector space spanned by x1 to xn. So the power series ring is, instead of direct sum, you take products. You guys remember the difference between direct sum and product? For a direct sum, we only take finite sums. But then for the product, it's just infinite tuples of coefficients, right? So for a polynomial ring, right, it's an expression in x's that stops. The power series doesn't stop, and you just don't care about convergence or anything like that. So, the product is what you think it is, right? Like if you have an expression here, let me write it down. Let me use this sort of multi-index notation. Right, suppose you have some multi-index like that. This is a power series that goes forever. Well, I suppose I should say something like this. And I multiply it by another one. It's going to be j xj. And this product here, what you do is what you think you're supposed to do. You just let algebra be itself. So this is a sum over the indices k, right? And so, but what goes here is that you're supposed to look at the sum of ai, bj, and what you want is I plus j equals k. This is the coefficient, right? So it's just, how is it called? Like when you expand an expression, you just add all of them together. And this is well defined, right? You may be saying, okay, but we're talking about infinite sums, what's going on there, right? Like that's a concern. But to write down this sum, this is a finite sum, right? Because what you look is that you fix a k, a multi-index, and you look at all the possibles I and j that add up to k, but there are finitely many of them. So this sum here is well defined. It's finite, right? So we are really doing algebra. We don't need to invoke any analysis to make this definition, right? Everything is a finite sum, and so it makes sense. And this is how you get these formal powers in this ring. And so the philosophy right from algebraic geometry, the more functions, the rings are supposed to be rings of functions in some space. And the more elements you add to that ring, the more functions you have, the more you shrink the space, right? And so here you added so many new functions, right? Because look at it's just ridiculous what you can write down here, right? The exponentials, therefore trigonometry, whatever you can possibly imagine is there in principle, especially if k has characteristic 0. So you added so much to your space that you shrink it as much as you can. So you're really looking at arbitrary infinitesimal neighborhoods around your point. That's what this is supposed to accomplish. And you can just do it algebraically like this without ever having to write an epsilon. And I think that's wonderful. Algebra is pretty wise. I think that's the upshot. People are not. So just trust your algebra and you'll be okay. I think that's more. Okay, so, and yeah, therefore, this is what you're doing to your space when you do this simplicious process. Okay. By the way, this is the same process that you use to get p-adic completions in the integers, right? If you have the integer z and you complete the prime number, you get the p-adic integers. It's the exact same definition. Okay, so well, I guess now I can tell you the definition of complete. Definition: R is complete if, when you complete it, you get an isomorphism. And let's say, like, for this to make sense, you want this completion operation to get important, right? Like if you have R hat and you complete it, you recover R hat. That's true, but actually you need R to be an integral for that to be true. So for this to make sense, so you need R to be an integral. So in fact, the completion of the completion is the completion, and let's say because R is an integral, okay? So because of things like this, is that I'm slightly afraid of non-Euclidean rings. Okay, so the next thing we need to talk about is characteristic. What is the characteristic of a ring? So this is the thing. Rings don't live in the absolute, They're all Z algebras. So Z is the initial object in the category of rings. In other words, there is the unique ring homomorphism from Z to any other ring. So all rings are Z algebras. They are defined with Z. Okay? And so this has a kernel. Right? You can compute the kernel of this thing. But Z, as you gotta know, is a principal ideal domain. Right? So this is generated by one single integer, right? But what is the choice of a generator here? It's n up to units of z. But what are the units of z? It's plus 1 or negative 1, right? So this generator here is ambiguous because you can have n or negative n. But only one of them is a natural number, is positive or non-negative, I'd say, right? So the characteristic, of the ring satisfies that it generates the kernel, but it is non-negative. In other words, it belongs to n. So these are the defining properties of the characteristic. Okay. So, for example, a ring has characteristic 0 if and only if z maps injectively to R, and so on. But it could have any characteristic, and that matters, and it matters a lot. So let's see. So for that, we need a definition of equicharacteristic ring. So definition. So R is equicharacteristic. Another way to think about the ring is just a whole bunch of fields glued together, right? What you're doing is you have the residue fields of R, and they're all glued together in R, right? So that's the algebra geometric perspective. And so what we're going to require is that we're going to look at the characteristic of the residue fields at P. Okay? Well, maybe a quick exercise. If I should do this. Quick exercise: if R is a domain, then the characteristic is either 0 or P, right? Because if R is a domain, then Z mod n, well, Z mod n is always inside, but Z mod, the characteristic, is always inside the ring by Noether isomer or whatever, right? Isomorphism theorem, right? But if R is a domain, Z mod, the characteristic, has to be a domain as well. And therefore, this has to be a prime, and the only prime ideal, so Z are 0, or the ones generated by prime numbers, right? So, in particular, when you come and look at here, these are 0 or prime numbers, right? 0 or prime numbers. But if you look at, for example, Z, look at Z, right? If you look at lines at 0, this residue field are the rational numbers. But if you look at lines at a prime number, the residue field is going to be Z mod P. And so you have a whole bunch of characteristics all mixed up. That's very difficult. So equicharacteristic means that these are all the same. So, but they have to be the characteristic of R in this case. So all fields they are. So the characteristics are not mixed, right? Otherwise, we say R. I'm not sure what is the verb here. Is equicharacteristic or has equicharacteristic? Not sure. So let's say has or is mixed characteristic. Okay. I'm going very slowly today. I just don't feel like going fast. I feel like that sometimes. Right? And here's an exercise. R has equicharacteristic if and only if R contains a field as a subring, okay? as a sovereign. In other words, R is an algebra over some field. One direction is easy, right? Like if R is defined over a field, its characteristic and the characteristic of all the rest of the fields have to be the characteristic of that field. This direction is easy, right? But the other one is more interesting. But essentially, it's the fact that if you want to invert an integer in R, right? If you want it to be a unit, it has to avoid all maximal ideals. So that's why. Okay, so that's why you see this hypothesis all the time in real polynomial. Or suppose that R contains a field, what you're trying to ensure is that the characteristic is the same everywhere. It's the same thing. It's an easy way to guarantee it, but it's the only way. That's the whole point. Okay, so and notice that when R is equicharacteristic, its characteristic is 0 or a prime number. It cannot be 6, something like this. Okay. Okay, why am I talking about all this? It's because of the following. It's the most important concept for what follows. Where am I? Here, blah, blah, blah. So it's a notion of coefficient ring. Now, we're trying to understand the structure of complete local ring. So suppose that you have a complete local ring. So what we're trying to find is the following. We're trying to find a subring, a local subring of R. Write it down like this. That is local and complete. So local and complete. Its maximal ideal is generated by P, where P is the characteristic of K. Let's put it here. P equals the characteristic of K. That can be 0 or P, right? If the characteristic is 0, therefore here we're saying that the maximal ideal is generated by 0, therefore this is a field, and it's actually equal to K. Okay? But if P is positive, then what you have here is a one-dimensional ring. It's a complete local ring. And also I want the expansion to be local. This is local. Right? Which means that if you take the maximal ideal of R and you contract it to this subring, you're supposed to get the maximal ideal of lambda. So this is the locality hypothesis that is there. And so whenever you have such a subring, local complete subring, this thing here is called a coefficient ring. How do you spell that? Coefficient ring. Okay? So that's the key concept here. To write down the structure of complete local rings. You are looking for a local complete ring such that its maximal ideal is generated by P and its residue field is K. Okay? And this is a local extension. Remember, local means maximal ideal contracts to maximal ideal. Okay. If P is 0, this is a field. So Let's make that remark clear. Let's go to the other side. Any questions so far? Perhaps on Zoom? I'm sorry we haven't talked about F-singularities yet. It's gonna come up soon. But we need all this stuff. So preliminaries. Okay. So what are the possibilities for a coefficient ring? So there are, if it exists, there are three possibilities for what it can be. So the easy case is that R has equicharacteristic. In that case, that's what I was saying. Lambda is a field. Well, is a field. It's a subfield, right, of R, right? Such that, so lambda is a subfield of R, and so when you look at the canonical map to the residue field, this is an isomorphism. So in the equicharacteristic case, a coefficient ring is nothing but a copy of the residue field inside R that maps canonically into it, which is the case, for example, for the case of power series ring, right? For power series, the residue field is K, right? Well, I forgot to say that the power series ring is local. The maximum ideal is generated by x1 through xn, and the residue field is K. But there is a copy of the residue field inside the power series ring, right? Now let's look at the mixed characteristic case. R has mixed characteristic. R has a mixed characteristic. And notice that if R has mixed characteristic, then so it means that the characteristic of K is prime. So if the characteristic of the residue field is 0, then the ring is equicharacteristic necessarily. So you have that the characteristic of the residue field is P, is positive. I guess non-zero. Let's put it like that. It's a prime number. And there are two cases depending on whether or not P is nilpotent in R. So we know that P belongs to well, it's not a unit in R, right? It belongs to the maximal ideal of R. And so there are two possibilities here. This is split into two cases. P is nilpotent in R. Let's say P as an element of R is let's say it's not nilpotent. When this is the case, then this ring here is a complete DVO. It's a discrete valuation ring. This is to say that the ring is regular, really, if P is not nilpotent. And these rings are referred to as Cohen's rings. Okay. complete DVR of mixed characteristic. For example, it could be the p-adic numbers. That's an example of a coherent ring. Actually, given any field, K of positive characteristic, there is a coherent ring, such that that's a residue field. For FP is the p-adic numbers. Okay? Or P is nilpotent. P in R is nilpotent. This is a pathological case. And so notice that for this to be, this is the case exactly when the characteristic of R is a power of n. That's what it means, right? And so in this case, this ring is zero-dimensional. It's an Artinian local ring. It's Artinian local ring. So it is zero-dimensional in particular. It has this non-reduced structure. Okay. So that's how the world is split here. So a coefficient ring can be of these three flavors. Either you have equicharacteristic. In that case, coefficient rings are fields. In the mixed characteristic case, they are complete DVRs and therefore one-dimensional. Or they are zero-dimensional, but they have this weird structure that are near Artinian local rings. Almost fields, but not quite. Okay. So why am I talking about this? Because that's the content, the existence of these things is the content of the coherent structure theorems. Okay, what time is it? Okay. Any questions so far with this definition of coefficient ring? Okay, let me. So the coherent structure theorem. I'm going to put it in version 1. Actually, there is a typo in the notes. I forgot the important hypothesis here, which is complete. This is theorem 1.25 in the notes, and I forgot the important hypothesis here, which is that the local ring is complete. So it says, take a complete local ring. Complete, remember, Noetherian local ring. Okay, this is the key hypothesis here. You want to know what on earth that could possibly be. That's what you want to do. And so Johan tells you, okay, first, then, let's say then, first, R has a coefficient rings. And this is the big part, this is the hard part. Any complete local ring has to be defined over a coefficient ring. And out of this, actually, this can even be left as an exercise almost. This is the difficult part to construct that. Once you have that, then you say, okay, there exists a surjective ring homomorphism from power series, okay, over lambda. I'm going to tell you what lambda is in a sec. Into R. So notice R, what this is telling you is that R is a quotient, right, of this ring. So you take this ring and then you take some ideal and you take the quotient, right? It's a presentation for R, if you will. Where, so let me move the screens first. Where am I? Yeah, where, what do you think lambda is either a field where lambda is either a field. This is the case in which R has a characteristic, or a common ring. R has mixed characteristic.
So part B says that if you take the lambda and the ring, so we can its completion is going to be the R ring or
Pardon? What is it? The second?
No, the part B. Part B says that if you take the ring out of lambda with its coefficients, then if we make the completion, or what does the double arrow mean?
This is the ring of power series,
Yeah,
with coefficients in lambda.
yeah.
So you have this ring, and it says that R is a quotient of that ring.
Oh, okay. Yes.
Okay. So if R has equicharacteristic, then this lambda is a residue field of R.
Oh, okay.
But if it has mixed characteristic, it is a complete DVR.
Okay.
With the maximum ideal being generated by P itself.
Okay.
Okay, and these are all the possible complete local rings. So it tells you what they are. They are all quotients of these rings. Okay. Any questions with this? So part of why I want to emphasize on this is that the way you think about it is that, well, I think we need the next ingredient to make sense of this, but the point is that all singularities are simply quotients of these sort of rings. Okay, so, and I guess that's the content of the next theorem. So let me move. Where is the remote? Okay, so I guess we need that blackboard. Go ahead and structure theorem 2. Have you seen this theorem before? Not so much. Okay, but it's good that we know that. So I think they are often bundled up together, but I'm separating them so it's easier to digest them. Go ahead and structure theorem 2. Now we look at that, and actually, something I haven't said is that this is a complete regular local ring.
Because it's power series.
Yeah, Well, it's because the maximum ideal is generated. So, for example, if this is a field, the maximum is generated by x1 through xn. But if it is a complete DVR, then it's like the maximum is generated by p through x1 xn, and that's a regular sequence. Or you can see that they agree with the dimension of the ring as well. So, but what else will be a complete local ring? So take a complete. So before, look at the hypothesis was simply a complete local ring. Now let's take it complete regular. Right? We want to understand what are those complete regular rings. Then there are two cases. If R has equicharacteristic, then R is isomorphic to a power series ring over its residue fields. Well, if and only if, because the point is that this is a complete local ring. You see, the only complete regular ring of any characteristic is the power series ring. Okay? If R has mixed characteristic? There are two cases. It's always more complicated. No way around it. So then R is either what you may expect. It's a power series ring over a coherent ring. So here lambda is a coherent ring. It's a complete DVR. Okay. This maximum ideal is generated by P. This happens exactly when, let me erase here. Let's make room for this. Okay. So this happens if P is a regular element of R, okay? Which is not, but it may not be the case. But if it is not, then we know what happens. So what you do is that you take a quotient of this, and then you write P minus F. So here F is in M squared. You see, this means that P is in the square of the maximum ideal in this ring. And so it's not otherwise. So this means that this is an n-dimensional ring actually, right? This is n-dimensional, this is n plus 1 dimensional. Because you have n, you have the nth dimension from here, but you also have P, giving you one extra dimension. Okay. So this is what in the literature is referred to. This case here, when this happens, is the so-called unramified case. So these are the unramified complete local rings. Okay. So these things together tell us that, you know, like the theory of singularities are simply quotients of these rings, right? But you have a unique source for regularity, which are these rings, and their quotients are all the possible singularities, right? So that's why this theory is deep. You know, if varieties in a sense are the study of quotients of polynomial rings, singularities is the study of quotients of power series rings. Okay. And there is one more, which is my favorite version of this, which is the normalization part of the picture. Look at this beauty. Okay. Okay, we have company. I thought I would go through this quickly, but it's really not happening. So I promised last time we would start with the Kunz's theorem, but I don't know if that's going to be the case. But if you haven't seen this, then it's good to go to it. So So this is the Cohen structure theorem, part 3. Okay. It says humbly, take a singularity, aka complete local ring, complete. Right? That's your definition of singularity, complete local ring. So such that you assume either R is equicharacteristic or has equicharacteristic, but if it has a mixed characteristic, let's assume that it is a domain or a domain. So this is to make sure, when you say that it's a domain, to make sure that the characteristic of the ring is 0. But a bit more. I haven't seen this theorem yet in mixed characteristic, removing the domain hypothesis. So I don't know what's happening there too much. I should look at the proof in the mixed characteristic case. But this is the biggest generality in which I know it. In the equicharacteristic case, R can be anything you want. It doesn't have to be a domain. So now, then look at this. Just look at this. Then there exists there exists a subring A inside R. Let me. There exists a subring, right? Don't be that bad. It's not a subset or a subring. The subring is such that A is a complete local ring. B so complete local ring. And so, but I guess it's part of but let me write it down here. You have this extension here, right? So it's local. It's a local extension, meaning that the maximum ideal of R construct to A, and automatically that induces an extension of residue fields, right? So if you have a local extension of rings, that lets you see that you have an extension of residue fields. So the first condition is that it's local and induces an isomorphism on residue fields. So you haven't changed the class, the residue field class, which really matters, right? So and it is generically a tau. It's let's say generically separable. In other words, well, we're going to see in a sec that let's suppose that, let me do the easiest case. This is going to come up later, but so suppose that R is a domain. That means that A is a domain. Well, for this to make sense, I forgot to say something else. Damn it. So part of what I wanted to say is that this is finite. Okay, I think green is a bad color. Let me do it in red. So this extension is a finite. Finite. Very important. It's finite, right? R is a finally generated A module.
Oh.
Okay, that's what it means. You know, R with this structure acquires an A module. So R is an A module, right? Because it is an A algebra. So I'm claiming that this is finite local ring. And so since it is finite, right? So suppose the case that in the case in which R is a domain, then the field of fractions of A is inside the field of fractions of R. And what this claims, this part here claims that this is separable. Okay? It's generically separable. So it's separable on residue fields. Separable, no, not on residue, sorry, on separable on fraction fields. And 3, and the third condition is the following. What am I doing? Sorry, I have to move too much. Let me maybe zoom out a little bit. I just wanted people on Zoom to be able to see both blackboards. And third, it's so good. Third, C, A is isomorphic to this. I think this is the part for which you need, like, in the mixed characteristic case that R is a domain, because if this were true, right, you can see that it has a coefficient ring that is a Cohen ring. And so, you know, like you rule out this third hypothesis that the coefficient ring is this Artinian thing. So, but in the equicharacteristic case, it's fine. So, so you can see that this third Cohen structure theorem is a formal method normalization, right? It says that any singularity in the world, let's say reducible singularity in the world, it's simply a finite extension of these rings. Right? In other words, like let's say that you only care about integral domains, for example. What this says is that any singularity in the world, let's say you only care about normal singularities. We're going to come back to that later. Then any singularity in the world is obtained by taking a separable field extension of the fraction fields of this, and then you normalize. That's all there is to it according to this theorem. Okay? So what this is telling you is that singularity theory in a sense is about the Latt theory of the field of fractions of this and its integrality with respect to this. So this is a formal method normalization. Which is gonna come up a lot. So this is a formal right? So method normalizations exist in the study of varieties, right? Any variety is a finite extension of an affine space, or define ones, or you say the projective variety is a finite cover of a projective space, right? And so here we have a singularity version of that. Any singularity is just a finite extension of a complete regular, of an unramified complete local ring. Okay. So they should put in perspective what the theory of singularities is all about, right? So it's good for you to know what are we studying here, what type of beasts we're playing with. So for example, this is super cool because, well, I'm going to say that in words. I left it as an exercise. It's going to come up a lot. But then with this, for example, you can understand what Cohen-Macaulay singularities are, right? Like we saw at the beginning of the class that the cohem-equality property is preserved under completions, right? It's a truth singularity property. And from this net normalization, you know what cohem-equality rings are. Because as an exercise, I'm going to let you show that R is cohem-equality if and only if any, therefore all of its net normalizations, this sort of things, are free, are flat, right? And that's beautiful, right? It's beautiful when you can understand any property, any commutative algebra property in terms of flatness, right? Flatness is think about like this refined notion of freeness, right? And here, this lets you translate cohem-equaliness into flatness. The flatness of what? Of a net normalization, right? Thanks to this. Okay. I'm going to tell you later what Gorenshin is in terms of net normalization. That's part why I love this net normalization business, because it lets you understand a whole bunch of difficult things in very simple terms. Okay. And therefore here you are. It's this theorem also lets you see why what the notion of regularity we have is a good one. So exercise. Look at this. So take R in a theorem. Right then, R is regular if and only if what you expect from, let's say, analysis happens, right? So, or from differential geometry or whatever you may want to say here. So R is regular if and only if when you localize at the prime ideal and you complete, right? You look at arbitrarily small neighborhoods around the point P in this spectrum of R, right? So this is isomorphic to, well, take the residue field of P, right? This is the field of fractions of R modulo P, if you will, too, right? And so all you have an Ethereum any characteristic. I'm going to let you write down the next characteristic here, which is just a whole mess, because sometimes there will be field, sometimes there will be something else, right? So, and then I guess here you have to use the dimension of the local range, which is the height of P in R for all P, right? So you have the spectrum of R, and around every point, it looks like some sort of a fine space, right? It's locally the same everywhere, modulo residue fields, right? Let's say that if you look at the, like for example, let's suppose you have a ring whose all maximal ideals have the same residue fields. Let's say an algebra of finite type, like over a very closed field, like the already type situation. That at every close point, the space looks the same. It's the exact same thing. It looks very, very affine, right? You see, so I think with this, you should be have a good grasp now of what a singularity is, right? Or what regularity only means, right? So that we have really a good notion. And of course, any notion of singularity is just a deviation from this. Okay. Any questions on Zoom, perhaps? Are we happy? Is this cool? Is this inspiring? It's pretty cool, isn't it? Sometimes one gets old and everything and tends to forget that there's a lot of beauty around, right? For example, these sort of results. You may think, oh, they're also basic, but it's quite substantial. There is a lot of math, going into this. Okay, so that finishes our discussion on regular rings. Okay, today I wanted to start the Kunz's theorem. I think we still have, do we still have any time left? I'm so sorry. I promised last time we would start with the Kunz's theorem, but I just didn't. I just decided to talk about this because we didn't do that last time, and I said, okay, read it or something. So we have some minutes left. There are no questions, so then let's start talking about what we're going to be talking about next time, the Kunz's theorem. So what we want to do from now on in this course is to understand deviations of this in the equicharacteristic but prime characteristic, okay? And the first ingredient is Kunz's theorem. So let's start section 2. Section 2 is about Frobenius and Kunz's theorem. So from now on, all rings are FP algebras. In other words, they have prime characteristic. Remember, this simply means that Z mod P equals FP is a subring of R. In other words, R has prime equicharacteristic, right? And of course, Euclidean. I'm always going to assume that. I'm just calculating this sort of stuff. And we see that if we're studying singularities, we are going to have to assume that anyways. Okay. So what does that mean? What this means is that you have your ring, right? And the following happens. So you take an element R of that ring, and you can raise it to the P power. This is a multiplicative operation, right? So R times S to the P, because the ring is commutative or associative or something like that, is something like this, right? We're all good with that. But this is the shocking part, and this changes everything. What happens if you write R plus S to the P? So, well, you expand, as you know, and this is, how does this work? This is X to the I minus, yeah, P minus J. No, what am I doing? I. It's very open, I just write. Yeah, okay, A plus J, right. At I equals 0 to P.
Yeah, and it's instead of X we have R, instead of Y we have
Oh, yeah. Sure, R and S. Sure. And so the point is like the first term of this, or the last one, I'm not sure, it's like R to the P. But then you have the sum from I equals 1 to P minus 1. P choose I, or I, S P minus I, plus S to the P. But if you think about it, this number here, this is divisible by P. Okay. Exercise or something. And so what you get is R plus P to S to the P, right? Which is a dream, right? It's a dream for any college student.
Yeah, from junior high.
So the binomial expansion is absolutely trivial. Well, the P binomial expansion. So what is the consequence? This is a ring homomorphism. is a rank homomorphism. Right, and that thing here is called the Frobenius. This is called Frobenius. And what we will see in this curve is that it dictates light and death. Positive characteristic. Everything is about it. So you better love it. So if it looks scary, but it's really a beautiful thing. And just to say what Kunz's theorem is the following, and that's what we're going to prove next time. I think we have one more minute. So this is the beginning of the theory of F-singularities, Kunz's theorem. Look at this. Take our always in the theorem FP algebra, right? So R is regular. Remember that I was saying like how beautiful the structure theorem is because it tells you like you can think of chromophobiness, freeness, or something. That's not what a Kunz's is. Kunz's theorem reduces regularity in prime characteristic to flatness of some ring homomorphism. So if and only if, what do you think? Frobenius is flat. So Frobenius captures the theory of singularities in prime characteristic. Okay, and what do you think F-singularities are? Well, are singularities in prime characteristic that are defined, but more than that are studied, are understood as deviations from flatness in Frobenius. Right? Because that's what this theorem says, that any singularity in prime characteristic is nothing but the failure of Frobenius being flat. And that's not the last name F-singularity. Okay? So next time we're going to prove this theorem in full detail. Maybe we're going to give 2 proofs, I'm not so sure yet. But yeah, so that's going to be for next time. Any questions? So I guess the course starts on Thursday. We finish the preliminaries here. Okay, goodbye everyone. See you Thursday. Oh, and well, there are office hours today at 2 p.m. But these are like actual office hours in the office, not on Zoom.